Hello and welcome back. In this video, we are going to understand. Okay, this is A-level Computer Science 9618, Chapter 1, Information Representation, and in this video, we are going to cover the subtopics which is sound and compression. Okay, so this is A-level Computer Science. (9618) and the subtopics are sounds, how they are encoded, and compressions. Okay, compression techniques, lossy and lossless compression, run-line encoding, etc. Okay, so these are the subtopics. So starting with sounds, what are sounds? Okay, so sounds are, sounds just like I'm speaking this microphone, it's a sound, and this sound is, it's converting into a digital format. So sound is an analog value, right? And and it needs to be digitized in order to store sound in a computer. Okay, and okay, let me write it down. So sound is a analog signal, is an analog signal, or you could say analog value. Okay, waveform, which is need to be digitized in order to store sound in a computer. Okay, so sounds are waveform like this, or wait, this is how it looks like, right? This is sound wave, and now you need to convert this in digitized form. In order to do that, the sound will be sent in a AGC, which is analog to digital converter. Okay, and then this will give digitized format, I mean 1 and 0. All right, now we want that sound we want that sound to be heard from a loudspeaker. Okay, so in order to do that, so we can, sound is produced from a computer by passing the digital data through a DAC. Okay, so here it comes, DAC, which is digital to analog converter, and then from ASC again, it's converted to analog input. Then we can use an amplifier, and then it will be amplified, and there you go, we can heard voice from a loudspeaker. Or right now you may be hearing my voice from your speaker, right? Whether you are watching this on a laptop, on a mobile phone, or anywhere else, anything, so this is how it is. So right now I'm a speaker, right? I'm sending analog value into the microphone, and then it is converted and then it is going into the conversion, analog to digital converter. It is stored as a binary value. Okay, then now we want to listen this sound, so we go to digital to analog converter. We got the analog signal back, and then we try to amplify it to increase the amplitude of the sound, and then we can hear it from a speaker. So this is a speaker. The second point is sound is produced from a computer by passing the digital data through a DAC, and then through an amplifier, then finally the sound emerges from a loudspeaker. Okay, so this is how you do it. Sound wave, ADC, digital, stored in digital form, then DAC, amplifier and speaker, going from this from here to here. But what we're going to focusing on, in here, that how they are represented, how do these, how they are encoded. Okay, how sounds is represented and encoded. So we need to understand that how does it work, how does sound is represented and encoded in digital form, is broken down into thousands of samples per second. The sound will be sampled at a set time intervals, and these sample values form the binary values which form the sound file. Okay, so digital sound is broken into thousands of samples per second. The sound will be sampled at a set time intervals, and these sample values form the binary values which form the sound file. Let me show you a graph. Let me make a graph for you all, so that we could understand this, what I really meant by that. Suppose that this is a graph. Okay, or not, this is a graph. Then we have this wave. Okay, so this is a wave. Then now here what I'm doing, I'm taking a sampling from here, taking each sample, taking samples from different set of interval of time, here, and here, and then here. This is what I'm doing, I'm taking a sample. Okay, and then after taking a sample, we are storing in bytes, storing in bytes. Okay, so you are taking samples and then you are storing in byte form. You are storing as bytes. So this is a byte, and let's say this is 1101, this is 1100, this is 1011, 1010, 1001, 1. Okay, so it keeps on going like this. 0 1 1 1, 0 1 1 0, 0 1 0 1, and etc. and 0 1 0 0. Okay, so you are storing first of all you're taking a samples. So let me write down the definition of what is really a sample. Sampling. What is sampling? Okay, I think we don't have the space here. Let me write it down in here. What is sampling? Maybe in here. Sampling. Okay, so what is sampling? Sampling is amplitude of sound wave taken at different point in time. So this I'm taking sampling of these, I'm taking a sample from a different time interval. So this is time, actually different time interval I'm taking sampling, and I'm storing in a byte. Okay, so what is sampling rate? Sampling rate is number of samples taken per second. This is what sampling rate is. Then okay, let me write it down. The number of samples taken per unit time. Higher sampling rate helps to get an approximation of sound wave. Result in more accurate digital representation. Okay, increasing sampling rate. If you increase the sampling rate, then it will be, sampling rate is directly proportional to small quantization error. Okay, I'll tell you what is quantization error later. For now, let me write down. Rate is directly proportional to accuracy of the accuracy of the recording. Okay, so if we increase the sampling rate, then it will look something like this. Let me show you how. Let me make another graph. Okay, now this is a wave. Okay, but if we try to take the samples, then it will look something like this. Okay, so this is how you're taking a sampling. This is how you're taking a sample, right? There's a gap between these. You can see here there's a gap, because we are taking a sample, like this. We are taking the sample again, sample. Give gaps. Let's just assume that this is a low sampling rate. Okay, taking the number of sample per unit time. Okay, this is so low sampling rate. If it was a higher sampling rate, then it will look something it would look more detailed. Let's say if, for example, this is another wave, and if it has a high sampling rate, then it will look something like this. It will look like this. Increasing sampling rate. Something like that. It will be taking so many samples per unit time, in a given time, taking a samples. But if it have a low sampling rate, then it will look something like this. This is a low sampling rate. Okay, so having a high sampling rate means having a better accuracy of the recording, and higher sampling rate also helps to get an approximation of a sound wave, resulting in more accurate digital representation. Okay, this is what sampling rate means. Okay, like for example, this is the example. High sampling rate was low sampling rate. This is low sampling rate because we are taking samples. We are taking low samples per unit time. Taking this samples, then this one, then this one. This one, and then this one. but you are taking so many samples, and this now you can look at that. It's a beautiful approximation of the wave. Okay, so high sampling rate helps to get an approximation of a sound wave, result in more accurate digital representation. And in here, low sampling rate, high sampling rate, taking low samples per unit time, taking high samples per unit time. Okay, this is a difference between low sample rate and high sample rates. Okay, now let me just delete this sampling rate. Now let's move forward to what is sampling resolution. Let's take this one, sampling resolution. Okay, what is sampling resolution? Before going to sampling resolution, what is quantization error? What is quantization error? Let me discuss this. Quantization error is, it means that having a difference between the analog signal and the closest available digital value at each sampling instant from the analog to digital converter, AD converter. So quantization error is nothing but having the difference, getting the difference between the analog signal and the available digital value. Okay, so high sampling rate, which means very small quantization error. Okay, the greater the sampling rate, the smaller the quantization error. You can see here there are gaps. This is the quantization error, this is the quantization error, this is the quantization, because we are having gaps and it's not a complete approximation of the sound wave. Okay, there is less quantization error because it's a complete approximate, having sampling rate between small quantization error. Okay, now let's move forward. What is sampling resolution? Okay, the number of distinct values available to encode represent each sample. The number of distinct values available to encode or represent each sample. In simple term, okay, so you can also call it as the bit depth of the sound. You can call it sampling resolution or a bit depth. So what is sampling resolution or bit depth? This is sampling resolution. This is sampling resolution. Okay, or you can call it bit depth. The same meaning. So if we try to increase the sampling resolution, it means that we are giving more spaces. We are giving more space for the samples collected, because every time you try to take samples, multiple samples taken at a time, then you need to store those sampled values, right? So high sampling rate, which means you need a high sampling resolution. Okay, it's the same thing like, for example, having a hotel. Okay, in a hotel there are so many rooms, like 250 rooms, and you're trying to attract customers to come into your hotel. So, and they are making a booking, let's say per hour. So how many customers are booking the rooms per hour? I mean, for example, let's say 25 have booked a room per hour, and they are staying in a hotel. An hotel and a hotel have at least 250 rooms. Okay, so 250 rooms available spaces for the people. So 250 rooms is sampling resolution, and the number of people coming and booking their rooms per hour is known as sampling rate. Same thing here, you are taking a sample per unit time, and then after taking a sample you need to store those sampled values. Okay, this is how it is. Okay, so this is a bit depth of at least 2 of power. So this is a bit depth of 2. Okay, you can, if you increase a bit if you increase the sampling resolution, or you can call it bit depth, then it will give a more accurate representation of a sound, more dynamic range, and smaller quantification error. Okay, let me write down all the points. The point one is the number of distinct values available to encode or represent each samples which have been taken. Number two is number of bits used to encode the data for one sample. Okay, specify the number of bits used to encode the data for one sample. A large number of bits, it's the same thing as we have discussed about images, and they have a bit depth, bit color, bit depth color, and same thing here, bit depth, which means 2 of power n. This is a bit depth. Increasing the number of bit depth, which means increasing the rooms for the available samples. The more bit depth, the more the sampling resolution, the greater the space available for the samples being stored. Okay, and another point is that if for example if you have a 16-bit resolution, which means that you have 2 of power 16, at least 65536 number of distinct values available for each sample. Alright, and increasing the sampling resolution means so if you increase the sampling resolution, then it will get the more accurate representation of sound. Same thing as sampling rate. Sampling representation of sound. More dynamic range. It will give more dynamic range. And it will give small quantification error. Okay, and small quantification error means, what does it mean? The difference, having the difference between the original analog signals and gated discrete value digital signal. All right, this is what it means by quantification, having the difference between original analog signals and the digital signal. That's what it means, right? Yes, the difference between the overall analog signals and the digital value signals. Okay, this is known as quantification error, and if the more sampling resolution there, the smaller the quantification error. Okay, and quantization error means difference between the analog signal and the available digital value at each sample. We're talking about each sample from the analog to digital converter, each sampling. But this here means overall original analog signal and the replicated discrete value digital signals. Okay, so here we have this bit depth resolution, which means sampling resolution. So we have at least 1 2 3 4 5 6 7 8 9 10 11 12 13 bit depths, or you can say available space for the samples, storing the values, but increasing the bit depth, which means more available space for the samples, and the more you increase it, so we need to make sure that we have an increasing the bit resolution, bit depth, or you can say, sampling resolution. Increasing the sampling resolution, also we need to increase the sampling rate. And only then we can have a complete accurate representation of a sound. Okay, so yeah, accurate representation of a sound. This is sampling resolution. Okay, increasing the sampling resolution, which means more space left for the samples. So this is what it means. Alright, and what happens, okay, so what are the benefits and the drawbacks for increasing sampling rate and increasing sampling resolution? What are the pros and cons? So the benefit is larger dynamic range, better sound quality, and less sound distortion. Okay, and the drawback is produce larger file size, takes longer to transmit, download sound file, like you're downloading a music from a website. If it has a bigger sound file, then it will take a lot of time to download it. Okay, and last but not least, requires great processing power. Alright, here we are. This is applying for both sampling rate and sampling resolution. If having a greater sampling rate or greater sampling resolution, obviously it will increase the file size, it will take longer to download, and it will require a great processing power. And as for the benefit, it will have a high quality sound, have less sound distortion, less noise. Okay, one more thing I forgot to tell you guys about, that small quantization error is also means noise, having noise, it also means that small quantization. So it will have less and larger dynamic range. Okay, so this is sampling resolution and sampling rate. This is sampling, and now what left is what is bit rate. Commonly it is most commonly used to convey the quality of compressed audio formats such as MP3 in kilobit per second. Okay, higher bitrate means better quality. Bitrate is directly proportional to audio quality. Okay, the higher the bitrate, the better the quality of the audio quality. Okay, and that it tells us that how many bits of data are processed every second. Bit rate is equal to sample rate multiplied by bits per sample multiplied by channels. Okay, so this is how it is. This is the formula. Now let's do the question for the bitrate in order to understand more clearly of what it really is. So let me write it down the question. So now we need to calculate the bitrate. So I'm calculating right now. Thus, a typical uncompressed high quality audio file has a sample rate of this 16 bit per sample, which means the sampling okay, so bit rate is equal to, and this is the sampling rate and this is the sampling resolution. Sampling resolution. Okay, this is sampling resolution and these are the channels. The bit per sample is the sampling resolution. Okay, so we have the 16 bit per sample, which means 2 of power 16. It's the bit per sample, or you can call it sampling resolution. All three are the same thing. So the sampling rate is 4416 multiplied by the bit 16 bit per sample, which means 16 bits representing one sample, multiplied by number of channels, which are 2. So it will be 14120 bits per second. But if you want in kilobytes, then you can just divide this by 1000 and it will be 1411.2 kilobyte per second, kbps. Okay, and let's say that that the song is 4 minutes long. It's 4 minute song is 4 minute long. What is the file size? What is the file size? Okay, so it is 4 minutes long, which means 240 seconds. So multiplying this, 1411200 multiplied by 240 seconds, and so it will be 338688000 bits, or you can call it 40.37 megabytes MBs. Okay, so this is how you calculate the file size of an audio file, and this is what a bitrate is. The number of the bit per second. The bitrate is how many of data are processed every second. So this is the bitrate, and this is a complete information about what are sound, how they are encoded, and we have discussed all the terms like sampling, sampling rates, sampling resolution, analog and digital data, and yeah, that's it. And what are the impact of changing the sampling rate or sampling resolution, we have also discussed that, and how to calculate the file size as well. So sound is done, and now what's left is compression. Now we are coming to compression. So this is the whole theory of sound, which we have completed, and now we are coming to compression. Now let's start with compression. And in compression we will learn the compression techniques. Okay, so number one would be, okay, so first of all we need to understand about what is the use of a compression, why do we use it, and where do we use it. The second thing is about lossy compression. Lossless compression. Okay, and justify the use of a method in a given situation. We need to understand in which situation can we use lossy compression, or in which situation can we use lossless compression. Alright, so understanding of how a text file. Okay, we also need to understand that where can we use text file. Okay, we can use a text file in lossless compression. I will tell you later why do we have to use it here. We use the lossless compression for text file. As for bitmap images, we also use it in lossless compression, bitmap images. We can also use it in here as well, bitmap images. Okay, and as for vector graphics, they are used in lossless compression. And as for a sound file, they are used in lossy compression. And then after that, we will also going to understand about run length encoding, which is also a lossless type of technique. It's kind of it's a complete it's also it's a different type of lossless compression. Okay, run length encoding. Encoding used for bitmap images. Okay, so let me just remove this. It is used for bitmap images. Okay, this is a different type of lossless compression. So let's start with lossy compression. What is a lossy compression? Lossy compression. So lossy compression is where the file size is reduced. The file size is reduced with some loss of information, and the original file can never be recovered. Okay, and we can use this in sound file because there are most of the sounds, most of the frequencies there that can be heard by a human ear. Okay, so we remove those extra meaningless memory. That's why about the image, the color tab, that how many different number of color could be produced by increasing the color tab. Okay, so there are certain colors which cannot be seen by a human eye. Okay, so we try to remove those particular pixels. That's why we can use lossy compression in here as well in order to save some extra memory. Okay, so that's why we use it in sound file and in image file. There are also other ways to reduce the image file, like for example, we can crop the image, we can decrease the color bit tab, and we can also reduce the image resolution. I'm talking about the image file, the bitmap images. Okay, we can, or maybe vector images as well could be, but I think no, I think it's all about bitmap images. Yes, crop the image, we can crop the image, we can decrease the color depth, bit depth, or we can also reduce the image resolution. Okay, talking about the image file. Now what is lossless compression? Alright, so this is what a lossy compression really is. Okay, now let's move forward to what is lossless compression. So a lossless compression is where the file size is, the file size is reduced, but no information is lost, and when necessary, the process can be reversed to recreate the original. And maybe that's why we are using the lossless compression in text file, because if we try to do this in lossy compression, then maybe some of the words could be vanished, it would be meaningless. So we use it for lossless compression. As for vector graphic, we also use it for lossless compression. Okay, so how do we use the lossless compression in vector graphics? So in order for vector graphic to be compressed, it must be in the SVG file format. It must be in SVG file format that are defined. They are defined in XML text file, which therefore allows them to be compressed. Okay, so let's run length encoding. It is a different lossless compression that can be particularly effective. They are particularly, it is particularly particularly effective for compressing a bitmap file. Okay, the compression converts sequence of the same bit pattern into a code that defines the bit pattern and the number of times it is repeated. It looks for run consecutive pixel of the same color, store the color value once, and the number of times it occurs. Reduce the size of a string of adjacent identical dots, such as repeated color. The thing here is we can also use runline encoding for images and as well as text file. Okay, so we can also use runline encoding to compress text file. Okay, let me show you how. Let me give you an example. For example, let's suppose that you have this text data like this: A B C D D, and now you need to compress this. So first of all, we're going to count at how many times it has been repeated. So it's 5, this is 4, this is 2, this is 5. So this one 5, A is repeated 5 times, so 5, and writing the ASCII value of A, which is 97. Okay, then B is repeated 4 times, so 4, then ASCII value. C is repeated time 2, ASCII value is 99, and D is repeated 5 times, and the ASCII value is 100. You don't need to remember the ASCII value, or maybe you should, but it doesn't matter. I think you should. No, you don't need to remember the ASCII values code. Okay, they may give you the chart of that, what is the value of this and that. The ASCII value of A is 97, and the ASCII value of B is 98, 99, 100, etc. Okay, so this is runline encoding. This is how you do the compression. Total characters of A, and this is key. This is the ASCII of A. Okay, and as for images, this is a similar thing we do with images as well using runline encoding with images. Okay, like for example, there are so many black pixels, then white, then black. So how many black are there? There are at least 6, and the color code would be, okay, you will be given the color code, don't worry about it. Let's say you'll be given a box, and inside it will be color symbol, which is W and B, and the color code then in binary form is 153 or no 255 for the white and 153 for the black. So color code binary, you will be given some details. Then using this we can write it down. So total number is 6, and the color code of black is 153. Okay, how many are there? 3. Color code is 255. How many are there? 2. Color code is 153. So this is runline encoding. This is how you do runline encoding. Similar thing is happening in here. Alright, and that's it. This is complete. This is compression. Thank you so much for watching, and I hope I'll see you guys in the next video. So congratulations, you have completed the first topic of A-Level Computer Science 9618. Chapter 1, Information Representation, is done. Now moving to Chapter 2. Okay, and the Chapter 2 is, Chapter 1, Information Representation, is done. Data representation, multimedia, compression, all done. Now moving to chapter number 2, which is communication.